Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be discussing on the general theory of small oscillations. This is going to be part 1 of our discussion. So where we will talk about the motion of bodies experiencing small oscillations about the point of equilibrium. So general theory of small oscillations. So this is part 1, right? So the key concepts are small oscillations near stable equilibrium, and we are talking about normal modes, and we are talking about stable equilibrium here. Okay, so let the system S be a mechanical system. Let S be a mechanical system with n degrees of freedom. Right? And we have with the generalized coordinates q1, q2, qn. With generalized coordinates q1, q2, qn, q1, q2, qn, and suppose S is conservative. Then the system is governed by the Lagrange equation. Then the motion of S is governed by d dt of partial t partial qj dot minus partial t partial qj is equal to minus partial v partial qj. So this is our regular Lagrange equation for each particle j from 1 to n. And then let us say we specify some initial condition. So let us say q 0. This is our initial condition in the configuration space. Configuration space. Right? So this is in an equilibrium. Let us say this initial condition is an equilibrium if and only if it satisfies, of course, it satisfies Lagrange equation. It satisfies the Lagrange equation star. And then we can write down for a standard system, we have that T is given by summation j from 1 to n, k from 1 to n, tjk. We are writing the general form of kinetic energy, tjk qj dot qk dot. And then for a Lagrange equation, the LHS can be described as follows. So if we plug this formula for the kinetic energy in star, we see the following equation. So LHS of star, we see that this is going to be 2 times summation k from 1 to n d tjk qk dot plus tjk qk double dot, and this is going to be minus the second term here. This is going to be summation j from 1 to n, summation k from 1 to n, and partial t jk, partial qj, and partial qj, the last two variables being qj dot qk dot, right? So this is what our right hand side is, and then we expect that the right hand side of our Lagrange equation of motion is partial v partial qj, right? And now so we what we have is that this is going to be 0 because our this is at our initial configuration q0, and that is because q0 is an equilibrium configuration, and we expect that in equilibrium configuration the velocity the potential is stationary, right? And so what we have is, or in other words, the equilibrium configuration of a conservative system are going to be stationary points of the potential energy V of Q, right? So this is a stationary point of a potential energy V of Q. Okay. So that is what we have. Now suppose Q of 0, if my Q of 0 is the notation is Q superscript 0 here. If my Q of 0 is an equilibrium point, suppose this is an equilibrium point of S in the configuration space, right? So what we see is that in the Hamiltonian space, what we have is our corresponding variables are q0, 0, right? So P is the conjugate momenta being 0. So then we have, this is the equilibrium in the Hamiltonian space. So then, so what we have is, so then we can describe before we move ahead, let us describe the concept of stable equilibrium here. So stable equilibrium. So the idea is, if the radius so what we have is that, suppose we are given a region where this trajectory is starting, right? Where this trajectory is starting, let's say this region is C delta, right? And and suppose these trajectories are all bounded inside a region C capital delta. That is, eventually they all, they all roam around, but they eventually converge inside a new region C of capital delta, which is again a bounded region. We are talking in the Hamiltonian space, Q comma P, right? And what we see is, the idea of stable equilibrium is that, suppose our radius, we need to find this radius small delta sufficiently small enough such that whenever the starting point of any trajectory is inside this region C small delta, the ending trajectory always remains inside this outer bounded region, which is C capital delta, right? And this capital delta will depend on the choice, which is the small delta. So what we have is, so we consider the equilibrium radius. So suppose the equilibrium radius is such that the radius delta goes to 0 as small delta goes to 0, then the equilibrium point q comma 0 is said to be stable, right? So any mechanical system performs small oscillations near the position of stable equilibrium. Okay. So then what we have is, suppose our minimum of the potential energy is we saw that the minimum of the potential energy is, we saw that the critical point of the potential energy is the position of equilibrium, and we further have that the minimum out of this critical point, the minimum of this stable equilibrium, minimum of this minimum of this critical points of the potential is going to be stable equilibrium of the system. So that is the statement. So the statement is in the form of a theorem that the minimum point of the potential energy V of Q are positions of stable equilibrium of S. Okay, so we can quickly see the proof of this result. So without loss of generality, we can assume minimum of VQ is at Q equal to 0, or V of 0 is 0. We can assume the minimum, the absolute base of the potential to be at the generalized coordinate Q equal to 0. If not, we can shift the potential, right? So which means that my kinetic energy will be T of Q comma P is T of Q comma P, and my total energy E of Q comma P is going to be the kinetic energy plus the potential energy given by V of Q, right? So since what we have is that this kinetic energy is going to be non-negative, this is for P non-zero, this is going to be non-negative, we expect that, and the minimum of the potential is 0, and the minimum of kinetic energy will also be 0, we expect that the minimum of energy will be also 0, right? So let me write this statement. So we expect that 0 comma 0 is the minimum point of this energy E of Q comma P, right? Minimum point of this energy functional. And we expect, we already saw that the minimum of this energy is at the point, the Hamiltonian phase point 0 comma 0, and which is equal to 0. Now if we take any other point, let's say inside, we can argue using that small delta capital delta definition argument, that if we take any other point sufficiently close to this origin and allow the point to traverse along a trajectory, then we can arbitrarily choose this original this neighborhood of the origin small enough so that the final point of this trajectory going to be will remain in a bounded region, right, in a finite region. So the same argument holds, and then which means that if we take any point sufficiently close to the origin, then the energy is going to be necessarily going to be greater than or equal to 0. So 0 is the absolute minima, or the point of the minima of the potential is going to be the minima of the energy of the system, or we found that this is the point of stable equilibrium, right? Okay, so via the equilibrium. Okay, so then let us look at this idea using an example. So consider the double pendulum. So we look at this example of a double pendulum. This is moving under uniform gravity, and we show that the vertical, this is the vertically downward configuration is a position of stable equilibrium. We have to show that this is the case for the double pendulum. So this question, this is something we have seen in one of our previous module. So the double pendulum is as follows. So we saw that the pendulum is as follows. So we have this mass m, this is phi, and this is theta, and we see that the original length between the two masses are fixed. So we have B and C. The two masses have capital M and have masses capital M and small m, and we see that in this case the potential energy of the system, this is recalling our result from few modules back. The potential energy of the system V theta comma phi is m plus m g b 1 minus cos theta, right? And this is going plus m g c 1 minus cos phi, and we see that we can write down the Hamilton's equations. Well, for that all we need is to find the right hand side of the equations, the Hamilton's or the Lagrange equations, the right hand side. So the right hand side, we have two generalized coordinates theta and phi. The right hand side boils down to dv d theta. So this is going to be small m plus capital M times g b. B and C, these are constants. These are the length of the strings attached to the support with the mass and between the two masses. So GB sine theta, this is 0, and partial V, partial phi, this is 0. So then this is when theta is equal to phi is equal to 0. Right. So when this is the case. Okay. So these are the two cases. So this can only happen when this happens, theta is equal to phi equal to 0, and we know that this is also if we look at well, by definition, since they make the derivative of the potential to be 0, these are my stationary points or critical points, and we also see that if we choose any other value of theta and phi and look at this potential, we will see that the value of this potential will always be greater than the value evaluated at 0, 0, which is 0, 0 value is 0. So the potential is always non-negative for theta other than the value at the origin. So which means that we have already found the result that the vertically downward configuration is a position of stable equilibrium because the potential is the minimum potential, right? Okay. So then let us now write down what is the alternate forms of these potentials in the form of for bodies experiencing small oscillations. So one example is bodies. This is the entire discussion of this module, that is bodies undergoing small oscillations about the stable equilibrium. So approximate form of T and V, you know, for bodies experiencing small oscillations. So let us say, so we expect the small oscillations to happen about the minimum of the potential. So small oscillations will happen about the minimum of the potential. The small oscillations happen about this point, right? And we need to find the approximate equations governing these small oscillations. So need to find approximate equations governing such motion. Approximate equations governing such motion. So again, let us look at the case of double pendulum again, the previous example. So in that case, our kinetic energy T theta comma phi is half capital M B theta dot square plus half M B theta dot square plus C phi dot square plus 2 B theta dot C phi dot times cos of theta minus phi, right? And V of theta comma phi is the corresponding potential. So M plus M GB 1 minus cos theta plus MGC 1 minus cos phi, right? And now we can write down the Lagrange equation, which we will eventually approximate. So the Lagrange equations, if we plug all these formulas in the Lagrange equation, we get back the following set of equations for theta and phi. We get two equations. The first equation is M plus M times B theta double dot plus MC times cos of theta minus phi times phi double dot plus MC sin theta minus phi dot square plus M plus M G sin theta is equal to 0. So that is my first equation. And my second equation is B times cos theta minus phi theta double dot plus C phi double dot minus B sin theta minus phi theta dot square plus G sin phi, which is equal to 0. So those are my two equations. And if we were to only retain the linear terms, so see, let us look at an approximate form of these two equations where we look at only the linearized terms, that is the non-linear or higher order terms other than the linear terms are dropped. So linearizing, we see that the following equations, we get back the following equations. So we drop terms like phi dot square terms or theta dot square terms, and we get the linearized terms, which are all these three terms. So 1, 2, 3, yes. And of course, this is another non-linear term sitting here, sin theta. So what we get is M plus M B sin B theta double dot plus MC cos of theta minus phi double dot plus M plus capital M times G theta is equal to 0. So that is our sin theta being approximated as theta for small oscillations theta. And similarly, we can use a similar approximation. We drop this third term, we approximate sin phi by phi, and we get the second set of equations. Well, the question is, we could have also got back the same set of two approximate equation if we had approximated our kinetic energy and potential energy by dropping all the nonlinear terms, right? If we had dropped all the nonlinear terms, that is, let me show you what I mean by that. So alternatively, this whole approach could have been done alternatively, that suppose V is half m plus small m g b theta square plus half m g c phi square, right? So if we use all these terms here, so if we linearize, we approximate cos theta, we approximate cos phi using the series, the Taylor series approximation, and retain only the higher order term, the highest order term, that is theta square and phi square, and drop retain the lowest order term and drop all the higher order terms. Then, and similarly do the same thing for the kinetic energy, and then find the Lagrange equation of motion, we will get back the same set of two linearized equations that we expected by doing the same exercise again. So the idea is that we could either find the linearized equations or the approximate equations by linearizing the energy, that is the kinetic and potential energy, or we could eventually linearize the Lagrange equation of motion to get the same approximate form. Either way. So I think I am going to end my discussion here, and in the next discussion we will be talking about some applications of these ideas of this particle undergoing small oscillations. Thank you so far for listening.